All right, to compute our repeated measures ANOVA with a single factor, that being group, we're going to examine the exact same data that we used for the one-way between subjects ANOVA. We sometimes just call it a one-way ANOVA in class. And we're going to interpret this data as different than we used to. So we used to think, okay, we're going to look at group 1, group 2, and group 3 as being a between subjects manipulation. 30, excuse me, I got a number stuck from a last video. 15 participants provided 1 point each. 5 were in group 1, 5 were in group 2, and a different 5 were in group 3. And we have our means and our standard deviations as computed before. So these numbers may look familiar, which is good. What we need to change in the way that we view this data and we view the group manipulation is we need to view this as a within subjects. So now view as a within little ss for subjects manipulation. So what we want to change now is that we want to see, say this is participant 1's row, participant 2's row, participant 3's row, P4, and P5. So what we did then is we imagined bringing 5 participants into our study, and each of them were in group 1, group 2, and in group 3, and they provided scores for each. So we had 5 participants providing 3 scores each for 15 observations. Big N is still 15. Little n, the number of observations per cell, is still 5. But the idea is now that the number of participants or subjects, if you're speaking just not in terms of them being people, but just abstracting a little bit. So our subject number is 5, but our observation number is 15. Before, when we were looking at data that was all between subjects, the number of participants or subjects was exactly the same as the number of observations. So here that's different. So just something to keep in mind. Now, because this is within subject manipulation, we are going to do something that's very powerful that allows us to examine differences between our 5 people, our 5 participants. And the way that we're going to do that is we're going to compute what's known as subject means, or participant means if you prefer to say it that way. So little s, subject means, right? This is not sum of squares, subjects means. I'm so nervous that it's just going to create some confusion. Let's be more, explicit. Subject means. Beautiful. All right, so we're going to compute those. So if I do the first one rather slowly, you look at participant 1, and they gave us scores 1, 2, and 1 across the 3 groups. So their mean score across all the groups, the score that really kind of encapsulates who they are as a person in this manipulation, is their the mean 1 plus 2 plus 1 divided by 3. And that gives me 1.333, and I'm going to keep my 3 decimal places for increased accuracy. Now, let's just examine this somewhat busy table together. So we have the group means here, 1.8, 3.2, and 7 for group 1, 2, and 3, and then we have the subject means here for subject 1, 2, 3, 4, and 5. So in a similar way, like the factorial between ANOVA, we're still using kind of marginal means, so to speak, because even though these are just group means with our single factor group, we also have this additional, it's not a factor, but it's an additional component to the analysis that helps us to understand that each person is different, and that is kind of expressed in the margin here for each row, the subject means. So let's take a look and make this table even worse. Let's look at P1 versus P5. So if you could still read that after I circled it. So 1.3 about was their mean across all the groups for P1, and then 6.3 or thereabouts for participant 5. And what you see here is a large difference between these two means. And so a big part of that large difference could very well be due to the fact that, well, participant 1 generally gives lower scores when they complete these group reporting or scores, and participant 5 instead, it happens to have these kind of larger means, and so the average mean for participant 1 versus the average mean for participant 5 is quite different. And this type of thing can mess up in ANOVA. This type of thing is not due to the group manipulation. It's due to the fact that people are different. So, I mean, if it's not due to the group manipulation, it'll end up in the error term. Where else is it going to go? It's a one-way design. So what the repeated measures ANOVA is going to do is it's going to create an error term for our F ratio, the denominator of the F, that will take into account these types of differences and not have them be part of that error. All right, so after all that, the idea is that we will still have a single F test for the within subject manipulation of group. It's going to be the mean squared group divided by the mean squared error. But as per our discussion, since the data are within subjects this time, this mean squared error will be smaller than the between subjects MS error, and that was actually equal to, rounded to 2 decimal places, 7.97. So it's just something to watch out for that. A lot of this will look very similar to the one-way between subjects ANOVA, but what's really going to set it apart is the way that error is dealt with and the way that differences between the individuals are dealt with. So what are we going to need to compute this F composed of mean squared group over mean squared error? Well, the first thing we need, of course, is the sum of squares group. We're also going to need the sum of squares subjects, which is made from using those subject means, the one that always ended in decimal places 0.333 or 667. Do you remember those? We're going to need to use those to create a sum of squares subjects. And the reason we need that is since our SS error is not just equal to SS total minus SS group, but we also have to subtract SS subjects. So I guess then we also need SS total. So in the end, we want our sum of squares group, and then we want the sum of squares error. But in order to compute the sum of squares error, we're going to need the sum of squares total, and we're going to need the sum of squares subjects. All right, luckily, when we computed the one-way between subjects ANOVA, we found the sum of squares group. It was 72.4, and this does not change with moving to our within subjects interpretation of the data, simply because it's the same data. So we still want to know if there is an effect of group on the scores. It's just that each person was in all 3 of the groups. And we also computed SS total, and again, since the data is exactly the same as it was when we did our one-way between subjects ANOVA, our total sum of squares is the same. So we have then the 168. So what's really changing is how we deal with the fact that now, since 5 people only contributed these 3 different observations based on the 3 different groups that they experienced, we want to account for the fact that those 5 people are in fact different people. So to do that, we're going to compute the sum of squares in the same way that we've been doing before, where we put a multiplier out, And then because we're comparing everything to the grand mean, it might help us to note that our grand mean, as it was before when we did our one-way between, is equal to 4 exactly. So first thing we're going to do is we're going to take the first subject mean, 1.333, and we're going to subtract 4 and square that. Our next subject mean was 3.333 minus 4, the grand mean, square that, and I'll just keep adding on another line. 3.667 minus 4 squared plus 5.333 minus 4 squared, and finally the largest mean, which corresponds to subject 5, 6.333 minus 4 squared. So let's break this down so that you understand where that 3 is coming from. So whenever we have these terms, these sums of all these squared deviations, what we need to account for is how many observations contributed to each one. Well, 3 observations contributed to subject 1's mean, as did 3 for subject 2's, 3's, 4, and 5 means. So there's 3 observations, number of observations, that were provided by each subject. Okay, and then because there are 5 subjects, that equals 5 terms. So here's the term from participant 5, and then here's the term from participant 1, for example, and so that's why we have the 5 terms in our SS subject formula. All right, so as we discussed before, when we want to compute SS error for the within subjects analysis, we have that SS error is equal to SS total minus SS group, but also minus SS subjects. So one way to interpret this quantity is it's the variance due to baseline individual differences. So the idea is that when we have the same data that was used for the between subjects ANOVA, we had an SS error that was just computed this way. So then what we say is that we remove the variance due to baseline individual differences since we have all of our participants in each of the groups, and that will create a smaller sum of squares error. So to compute the mean squared group, we do exactly as we did when we were computing the one-way ANOVA that was between subjects. We have our SS group, which is 72.4, and we're dividing that by the degrees of freedom. For a group, we have 3 groups, so it's the same idea. It's the number of groups minus 1. So 3 minus 1 is 2, so 72.4 divided by 2. And that is going to give us the same thing that we got before, 36.2. Okay. Our mean squared error is also computed as the sum of squares error divided by the degrees of freedom error. But in contrast to the between subjects one way with the same data, the sums of squares error and the degrees of freedom error will change. So let's compute that together. So sum of squares error we have from our computations is 50.933. And the way that we're going to compute the degrees of freedom error is we're going to look at the number of groups minus 1. And then that is going to be times the number of observations per group minus 1. So it's a little bit different because when we were doing the between subjects computations, we didn't have number of groups minus 1. We had just the number of groups. So here we're going to have 3 minus 1 times what's going to end up being 4. But before, when we were doing the between subjects degrees of freedom error, we just had 3, the number of groups, times 4. So we'll continue with that computation then. So that's 50.933, and that is divided by 2 times 5 minus 1, or 2 times 4. So this time we're dividing our sum of squares error by 8, and that's our degrees of freedom error, and the answer is 6.367. F ratios, as we know, are always computed by taking a mean squared of our effect, in this case the within subject's manipulation of group, and dividing that by the mean squared error, in this case the mean squared error that is left when we account for baseline individual differences from all 3 groups being experienced by each subject. So in math, or numbers at least, we have 36.2, which we computed before, and we're dividing that by our new mean squared error, which is 6.367 to 3 decimal places, and that ends up giving us 5.686. All right, now that we have that computation, we should compare the within subjects group manipulation and the final result from that with our before between subjects manipulation. So this is today, this is before. So we might report this as well with our degrees of freedom at 2 and 8 for group and error respectively. And that is equal to 5.69. I'm just going to round this F value to 2 decimal places. The mean squared error reported in APA style MSE is 6.37. It's gone now, but that's how we computed it. Oh, no, it's not. It's right there. Okay, so 6.37. And I'm going to guess that I'm pretty confident that if we looked up in the table, P would be less than 0.05. So I'm gonna bet some good money on that. And then for our long ago between subjects ANOVA with the same data and the same groups, just 15 subjects, we had F at 2 and 12 degrees of freedom, and that was equal to 4.54. So you note the difference, same data, but interpreting it as within subjects, we get a higher F value, which is more likely to achieve significance most of the time. And then we have our mean squared error again, this time it's 7.97. And we actually did examine F crit, or at least I did, and I told you that this between subjects ANOVA F was significant. So when you have the same data, it helps to kind of look at both what happens during a between subjects type of comparison, like a t-test or an f-test, and comparing that with a within subjects type of manipulation, or the data is the same, but we pretend the manipulation was within subjects. And what we can see here is that the degrees of freedom do lower a little bit with the within subjects computation, even though the data is the same. And that just means that when you're looking up the F crit, you're going to be looking it up for 8 degrees of freedom error instead of 12. So it's a bit of a trade-off, because smaller degrees of freedom error mean a kind of a bigger F crit. So it's harder to achieve significance with a larger F crit. But at the same time, the F value itself is larger because the MSE was smaller. So usually what ends up happening in this kind of case is, as you have more observations, not just 5 per group, you end up having a higher F statistic when you make your design a within subjects design. So I hope that was somewhat informative. Thank you so much, and we'll see you soon.